Hey, yeah, so welcome everybody to our second lecture within our course Federated Learning. Today, we complete our review of the basic machine learning setting. So this might be just a recap from most of you, but it's good that we're all on the same page then before we start in the next lecture on Wednesday to talk about the Federated learning design principle. So this is pretty much a extension or modification of the machine learning principle I will talk about today. It's yeah, so those of you who took my courses, this principle, this basic machine learning principle consists of three components. What are those three components of machine learning? Yes, very good. Data model loss. And in federated learning, we use a specific type or a specific representation for data and for models. In particular, we will use network structures, graphs. I call them empirical graphs, but I'm not too happy with this name. So maybe within this course, we come up with a better name for empirical graphs. Okay, so far so good. Are there any questions regarding the course organization, logistics? Yeah, again, after this lecture at 6 p.m. sharp, we will open the quiz for the first assignment. So this quiz is based on the concepts that I will now talk about, that you find in the lecture notes. And in the coding assignments are based on the solutions to the coding assignments. So you should have, or maybe some of you have already tried to work on the coding assignments. Are there any challenges so far? You can use your own computer using a Jupyter notebook environment on your own computer, or you can use the Jupyter Hub server from our department. Yeah. Regarding the coding assignments, please contact Alexander Pavliuk, who is the TA responsible for the coding assignments. I will also try to help you, but I might not be as good of a help as Alexander P, so to say. Okay. Yeah, then let's continue with the review of the basic machine learning setting. And yeah, please interrupt me anytime. I want to be this as interactive as possible. So let's see now. Finally. So we have data points, and we want to learn a hypothesis or train a model. So we want to learn a hypothesis, which is, for example, a linear hypothesis. So this is an inner product. And yeah, we already worked out in the last time. So this minimizing or learning a parameter vector by minimizing the average squared error. So we have here the squared error loss of the ith, or let's call it R. We use R to index the data points and I to index the clients in a federated learning setting. So this is a bit different now to my previous lectures. Yeah, and so far so good. So this is the training problem. And this is what I mean by a machine learning principle. So this is called empirical risk minimization, using a specific loss function, the squared error loss, and using a specific model. So this is one instance of the principle called empirical risk minimization. And we can rewrite this as argmin x times w squared Euclidean norm. And here this vector holds the labels, and then we have the feature vector here, feature matrix, which holds the feature vectors of the individual data points as its rows. Okay, so far so good. We can solve this. We will learn in the next lecture next week on Monday. we will learn gradient methods that iteratively compute a solution to this learning problem. So we start with an initial guess and we update it to a better approximation, and we update it again. And hopefully this converges close to the solution of this learning problem. So this we will look at in the next lecture, so next Monday. And here we will then see that these choices, in particular the feature vectors, they have a strong impact on the computational properties or aspects of this learning problem. So what are computational properties? I mean, in the end, we're interested in using as little computation as possible. So this means we want this to converge as quickly as possible, these gradient steps. So we will see then we use gradient steps for these updates, and we want them to converge as quickly as possible. And we will see that this feature matrix is crucial for the convergence speed. Does any one of you have heard or have some intuition? What do we want this feature matrix to be, such that these gradient steps converge quickly? So it turns out we can rewrite this problem, maybe just tell you this. So this optimization or this objective function here, f of w, can be rewritten as transpose q plus q transpose w, as we did already last time, with the matrix q being 1 over m. Okay, here we don't need this sum anymore. X transposed. And it turns out the eigenvalues of this matrix, they are the important characteristic. If those eigenvalues are close to each other, and we call those such matrices to be well conditioned, then these gradient steps converge quickly. Okay, but this is about the computational properties, and I will talk more about this in the next week's lecture about gradient methods. Any questions at this point? Okay, so for how many of you is this repetition? So you know this really by heart, really well, this setting, this machine learning setting. Okay, so still not for all of you. So it's not complete waste of time that I do here. Okay, so this is machine learning from the modeling perspective. So once you are at this point, you formulate the machine learning problem like this, it becomes optimization. It becomes solving this minimization problem. And maybe you have taken one or the other courses on optimization and convex optimization, and you have heard about some methods, interior point methods. In this course, we only use one type of method, which are gradient methods. And we will see we can get a lot of mileage only with gradient methods. Okay, but beside the problem or the challenge of actually computing the minimum in machine learning, we are also interested in statistical aspects. So I like to think of machine learning as a blend of statistics and optimization theory, or computational optimization theory. So the statistical question is this solution here, this actual hypothesis that I learn by solving this problem any good? Is this any good? I mean, if you have a very powerful model, meaning you can represent very difficult functions like such a function, and with deep neural networks, you typically can represent such functions, complicated functions, because you have so high-dimensional hypothesis spaces. And you will find one hypothesis that almost perfectly goes through your data points. So you can make the training error 0. And the problem is this can be highly misleading. So you're happy, you trained your model and it's 0 training error. You go to your boss and show proudly, I have trained my model, 0 training error. And what can be the risk then? What could be the problem? Overfitting, yes, because in machine learning, we always want to look beyond the training set. having zero training error is nowadays trivial because we have very nice computers with very convenient computational libraries, Python, PyTorch, to train very powerful models. So getting zero training error is trivial nowadays. I would say after 2012, after the deep learning hype, getting zero training error is trivial. It just means that you are able to correctly apply a PyTorch model or implement a high-dimensional deep neural network, which, by the way, might be non-trivial already. So this might already be challenging, but it's just the first step. So how can we look beyond the training set? And this is really the crux of machine learning and federated learning. How can we ever say something about a model that we train on a given data set beyond the training set? How can we ever know if the trained model generalizes beyond the training set? Yes, the validation set. This is what I will talk about in a second, and this is the most practical and most widely used approach still. But are there any mathematicians here who study mathematics or probability theory? So maybe one of the coolest applications of probability theory is, in my opinion, machine learning, because we can interpret data points. Why not? We can do it. Why not? We interpret data points as being draws from a probability distribution. So there is some hidden underlying probability distribution, and the data points that we see in the training set or that we use in the training set are just, in this case, two draws from this probability distribution. So we have a probability distribution, a joint distribution over features and label. And here we just have two realizations of this probability distribution. Okay. So once we interpret data points, and let's say, so this is called the IID assumption. And this is an assumption, as the name says, it's an assumption. Each data point, let's call it the rth data point, is a realization from this joint distribution. And how many of you have heard about this IID assumption? Yeah, some of you. So this is the bread and butter tool for analyzing machine learning methods. Because once you assume this or you subscribe to this assumption, why not? Let's say the data points that you see in reality, they are just realizations of an IID assumption. Then you can say, well, if I have, let's stick to the linear model. If somebody gives me a parameter vector for a linear model, so I define then a hypothesis map by this weight vector W hat, and I can evaluate the hypothesis for any given features. I can compute the average or the expectation of the squared error loss all of a sudden. And to do this, to define this, I need a probability distribution, of course. And this is exactly this underlying joint probability distribution. Okay. Any questions at this point? So I can now define, how do we call this? Let's call this risk. Let's call this risk of a given weight vector W. Okay, but still I need to, so to analyze this more, I would need to say something about the true label. So how is the true label really related to the feature vectors? And one popular model, and this is basically one example for such a joint probability distribution, is what I call a linear Gaussian model. So this, instead of specifying this probability distribution function in a closed form, we instead define it by a structural equation. I think it's called structural equation. So we say the label of a data point, of a realization of a data point, is related to the features by applying a weight vector, W bar. This is the true underlying weight vector, plus some noise. And this noise might be distributed Gaussian with zero mean and some variance. How many of you have seen such a linear Gaussian model in statistics? Yes, so this is popular. And once we assume this model, or it's just a modeling assumption again, we can work out this risk a bit more. We get for this risk, as also shown in the lecture notes, or noted in the lecture notes, a nice closed form, which is the difference in the weight vectors plus the variance of the noise. And so this is what we call an intrinsic noise or label noise. There's no way to learn these parameter vectors better if this model is true, is accurate, than sigma squared. This is the intrinsic noise in the labels. We cannot overcome this. Okay, any questions at this point? So these are a lot of assumptions. So basically it's Alex wish list here, because in reality you see data. I can put out any assumption that I want. Does any one of you know if we could test these assumptions? How can we test if the data points really conform to such a model? So, yes.
One way that I thought is maybe like making pairwise plots, like scatter plots, and seeing if the data points have linear correlation.
Yes, yes. So correlation tests. There are, if I remember correctly, there are established statistical procedures that allow to test. Does the data conform to this model, this linear model? And even at first place, is it really reasonable to assume that the data points are IID? And there are also tests for independence tests. So if you took courses from the math department, they have excellent courses on statistics, statistical models. There you will most likely hear methods for testing, for verifying if Alex's wish list here is any useful for a given application. And probably you should do it as an excellent machine learning engineer. Okay. What else is there to say? So the risk or the average in the sense of expectation of the squared error is given by this expression. So we have two components. We have the intrinsic noise. This is the intrinsic noise which no method can beat in general. There's no way to get an estimation error or squared error below this. And this might be nice. So this is something you could use as a baseline or reference. When you train machine learning models, you typically look at the validation error. And how we will talk about this in a second. How do you know if the validation error is optimum already? If you should continue or not? And if you have such a fundamental lower bound like the sigma squared here, this might be very useful for you because if your actual method, the average or validation error on the validation set, and it's close to sigma squared, then you are done basically. Then you can safely go to your boss. But the challenge is, first of all, is these modeling assumptions, are they accurate? So you should test if the data really conforms to this model. And second, I just written down the sigma squared. You also need to estimate it. So this is sigma squared is a parameter of this probabilistic model. And you can use, again, statistical methods for parameter estimation to estimate sigma squared. But you will rarely know precisely sigma squared, maybe with one exception. So in which case, in which setting or scenario, can you be really sure that this model applies. So the data points, they really follow this model, this probabilistic model, and you know the variance of the error. If you're a research assistant, you might come along these settings often. When can you be sure that the data follows this probabilistic model? Typically not for data that comes from the wild, but from data that you generate for the paper, for some research paper in the numerical experiments. So when you synthesize data, then you know it. Okay. So let me just briefly state one result that is also mentioned in the lecture notes. So about this training error or this error component here. So what can we say about the deviation between the learned parameter vector that we obtained from solving this linear regression problem and the true underlying parameter vector? And here we have the bound as follows. So the squared Euclidean norm is smaller or equal than the squared Euclidean norm of the error term divided by lambda 1 squared. So this is found in proposition 2.1 in the lecture notes, which also includes a proof. Yeah, please, whenever you find something fishy in the proof or in the statements, drop me a line. I'm really, really grateful for any feedback and hints for typos. Hopefully only typos. So this vector E, how did I define it? This error vector E is defined as minus 2m x transposed times n. And so this again is the feature matrix that we discussed before. And this vector here is the stacked vector, or the vector obtained from stacking all the noise terms from the training set into one vector. So we get one such noise vector for each data point, for the rth data point. So we have here the rth data point. The true label of the rth data point is the true underlying weight vector times the feature vector of the rth data point plus the noise, the rth data point. Okay, and what is lambda 1? Lambda 1 is the smallest eigenvalue of the matrix Q. So this matrix Q, again, just to write it here, is 1 over m x transpose times x. And this matrix is really important for not only for the computational properties, as I said before. So this matrix Q, defined via the features of the data points in the training set, not only will, as we see, define the speed of gradients, of the gradient steps, how fast they converge to a solution, to a linear regression solution, but they also are crucial for the statistical properties. The larger this eigenvalue, or the smallest eigenvalue is, the smaller will the training error be. Okay. Yeah, by the way, what can we say about this matrix Q? What special properties does this matrix Q have? Is it symmetric? So let's look at Q transposed. 1 over m is 1 over m, and then we use the rules for transposition. Yes, is Q. So it's symmetric. What else can we say? It's symmetric, and is it positive definite? It turns out that this matrix is positive, always positive, semi-definite. Which means for any vector W, this quadratic form W transpose times W is larger or equal than 0. Which can be easily verified, because if you multiply here by W and here by W transposed, what this expression here is the squared Euclidean norm of X times W. So this is always non-negative. which means this is positive semi-definite. And now maybe the most beautiful result of linear algebra, at least on the first courses here at Aalto, is the eigenvalue decomposition of positive semi-definite matrices. How many of you have those still in mind? Fresh. Yes. It's also called spectral decomposition. Spectral decomposition. Spectral decomposition of Q is, we can write Q as a sum of weighted rank 1 matrices, yes. So lambda 1 times U1 transposed plus lambda 2 U2 U2, that's a good name, U2 times U2 transposed plus until, so the dimension is W is size N. N transposed. And so we can find vectors U1 till UN and numbers, non-negative numbers, lambda 1, which are also ordered increasingly or non-decreasingly, such that this equality holds. And this is known as the spectral decomposition of a positive semi-definite matrix, and maybe the most useful result of linear algebra for the whole course. So if you have an urge to refresh your linear algebra knowledge, this might be good to look at, spectral decomposition of positive semi-definite matrices. We will come along this a lot during this course. Okay. Yeah, what I also need to say, so these numbers, these are eigenvalues. These are all eigenvalues of Q. They are non-negative, real valued, non-negative. And these vectors here, they are all, guess what, eigenvectors of Q. And they have the specific or distinct property that they are orthonormal. So the inner product between any two of them is 0 if K is not equal L. So they are orthogonal to each other, and they are normalized. So the norm of all of them is 1. So this is really a beautiful property that allows to do a lot of analysis. For example, come up with this upper bound on the error. Okay, so far so good. Yeah, by the way, is this this upper bound always valid? Can you use this for any data set? This iPad is very patient. I can write down whatever formula I like. So this lambda 1, what if this lambda 1 is 0? Doesn't work. So here we need some premises. If X, this feature matrix is such that the lambda 1 is larger than 0, then I'm safe. Okay. So this might not be always satisfied. Like the features that you get from the data points, they might all be 0. Then it's not invertible, and lambda 1 is 0. Okay. Yes, so this was to show you, to give you a sense of how you can analyze statistical properties of machine learning methods using a statistical model. And this is nice. You can work out closed form expressions for errors, and you can then look at, so what should I do to make this lambda 1 very large? Because it seems lambda 1 very large makes the error small. And then you could think of how should I shape the feature vectors such that this lambda 1 is large. And it turns out you can make this lambda 1 large if the feature vectors look like realizations from a wide Gaussian noise process. So this, for example, allows to motivate feature preprocessing methods or whitening transformations. Did anyone of you hear of whitening transformations yet? Yeah, this is something from my electrical engineering background, but it's related to feature preprocessing. So you get the feature vector for the rth data point, and you compute the new feature by standardization and normalization. And one reason could be to make this lambda 1 larger, so the estimation error goes down. Okay. So far, so good. But in practice, we might get along without any of these models, without any of these assumptions, and just as mentioned before, do validation. So we train a model. We train some model by minimizing the training error. And what we do after training, we look at the error at some other data points that we didn't use for the training. So this is called a validation set. So we train by minimizing these errors. And after we train, we get a learned hypothesis, for example, a learned linear hypothesis, Wx. And we compute then the resulting error on the training set. This is then what is called the training error, E train. This is the sum over the training set of the squared error times h. So the important thing is for the training error, we evaluate the trained hypothesis on the same data set that we used for training, that we used in empirical risk minimization. And this is very different from the validation error. Here we compute the average squared loss over a validation set that has not been used for choosing or for tuning this hypothesis H hat. But again, we compute the squared error. Okay. So are there any questions at this point? How many of you have tried or have used k-fold cross-validation in Python yet? Yes, very good. So this should be pretty recap for you. Is it good, for example, or is it often useful that I use this sequence or that I used sequential data points for the training set? So here, 1, 2, 3, and the last one for the validation set. So I now use the order given by the feature values. How should you split into training and validation set? Randomly, yes, as randomly as possible. So this is not good. This is for me now convenient, working on the iPad, the small iPad. It's convenient, okay, to have here the training set, but in reality, you should randomly pick one as validation set in this case. Okay, and then what do you do? So some of you already knew that you should compute the validation error. So what do you do then when you have the training error and the validation error? Comparing. So you compare them. Let's say we have a training error like this, a small training error. So I like to illustrate this with a bar chart and a small validation error. What should you do? You could go to the boss and ask, what should I do? Or what could you do? Any ideas? Sorry? Train again, yeah. Let's say you train again and it again ends up in this situation. So the training error is small and the validation error is large. This might point out that you have trained a very large or high dimensional model that is able to perfectly fit the training set, but doesn't care outside the training set, doesn't care at all. So what you could do is you could reduce the model size, make models smaller. How would that be implemented for a linear model? So let's say we have a linear model where we find the parameters for a linear map, and we have used the linear model and got this result. How can we make this model smaller? Yeah. How would you do it? You could, for example, instead of optimizing, of minimizing over all possible parameter vectors, you could fix some of them. You could say, I only minimize over parameter vectors where only the first two entries are non-zero and the rest is all zero. And this is equivalent to saying you ignore all features but the first two one. So reducing the number of features would be one way to make the model smaller. Okay. What else could we do? So we could make the model smaller. Is there another way to improve this situation? Okay. So you mean using more training data, essentially? Yeah, yeah. Okay, let's leave aside this shuffling, but more training data would be an option. And in general, the important ratio is the size of the model, which in our case, when we have D features and use a linear model, then this could be reasonably measured by D, divided by the size of training set. The number of data points in the training set. This D over M is an important indicator if we will overfit or not. And if this D over M, ideally we would like this to be much smaller than 1. And then typically we will not have overfitting. So we get rid of this high validation error. We will have a validation error on the same level as the training error. So let's say we have managed it. So we have done some iterations. We have tried to kick out some features. We have tried to collect more training data. So we have reduced D, increased M to make this condition satisfied. And now the training error is around the validation error. So when do you know that you're done, that you have solved the machine learning problem? Sorry? With a test set, yes. Yes, okay. Yes, very good. So when you use the validation set to change the model or increase the training set, then you essentially use the validation set also for model training. So let's say we then compute a test error. This is basically the final validation step, after which you don't change anything anymore. So this is then called test set or test error. And let's say also the test error is on the same level as the training error and validation error. So no overfitting, all good. How do you know if this is basically good, a good performance? Yes, exactly. That's what I meant before. You would need a baseline, and one way to get a baseline is a probabilistic model. But the challenge is where do you get a probabilistic model? Well, you need some intuition that for this type of data, such a linear model with this type of features might be accurate, but still you should test it like model fitting, statistical model fitting procedures. What could be another source for such a baseline? So this is very important. And it's very difficult to get a baseline or reference often. What could be another source for a baseline? Yeah, literature or some powerful machine learning model that you cannot use in your application because you have to run the model on a smartphone. But still, for comparison, you can use the model that is trained on a Triton compute cluster. Okay. So this comparing validation to training error is really a must. And also in your, if you do the federated learning projects, it should be discussed at least briefly in your report, the validation and training error of any model that you try out. I have discussed in the lecture notes these different scenarios. So when the training error is too large, when the validation error is too large, just to point out or to discuss, can it be that the training error is larger than the validation error? Yes, because you can be very unlucky, or I don't know if it's unlucky, it's just can happen. So you have a validation set that is like this, and you choose for some reason a training set that looks like this. And you want to fit a linear model. So then you will find for sure a linear model that goes perfectly through the validation set, but no linear curve passes through all training points. So you get validation error 0, but always training error larger than 0. So it might happen that you're very unlucky, that you do an unlucky split of your data points into a training and validation set, such that the validation error is smaller than the training error. How could you avoid this? There, I heard before, a strategy, shuffling, yeah, repeating this validation and training split several times, and then you average over this one unlucky split, so to say. That's why you typically do called K-fold cross-validation. So this is like doing K times this training validation split in order to average out any bad splits like this. Okay, in general, as a rule of thumb, how large would you choose the validation set? So the validation error, we use the validation set to compute the validation error. So let's say we have MV data points in the validation set, and we compute the average squared error. Average squared error. So how large should this MV be, this number of data points in the validation set? Any insights, any suggestions? What could we use to answer such questions? Yes, there was.
So what I've heard like on some courses is that often the validation set is 30 or 40% of the entire data.
Yeah. Okay. And why?
Because maybe I think a bit of convention, and then also like we want to have enough data to get a reliable model, but then we also want to have enough validation points so we get a good, so we can be reasonably confident that the model will well.
Yeah. Yeah, very good point. So we use the validation error as an estimate. What we want to estimate is the expectation over all possible realizations from this random distribution or probability distribution of squared error. So we want to estimate, we want this sum to be a good estimator for this expectation. Does any one of you know what type of results in probability theory study this approximation quality? So when does a sum of individual numbers that are realizations of a probability distribution converge to the expectation? How are such types of results known or referred to? Yes, the law of large numbers. The law or laws, there are different types, different flavors. Laws of large numbers. They study these questions. How large does MV have to be such that this sum is within 10% of this expectation with probability more than 90%, something like this. So such type of results you can work out using probability theory again. In particular, concentration inequalities or large deviation bounds. but we will not touch this in any detail at this point, in this lecture or course, even course. But just to tell you, there are some tools around. So it's not only trial and error. I mean, as pointed out, there are often these rules split 70-30%. But you should always be a bit critical or curious. Why? Why should I split it into 70-30? And one reason could be that this gives enough data points such that this law of large numbers kicks in. So this average over IID realizations is a good approximation of the expectation. Okay. Yeah, I suggest we have a break, short break till 5:10. Let's continue our review of the basic machine learning setting. Are there any questions at this point? Good. So we discussed now training and validation and how to diagnose a machine learning method by comparing training and validation errors. Yeah, we also discussed briefly how large the validation set should be in order to give an accurate estimate of the expectation of the expected squared loss. Yeah, sometimes it might be more convenient to do something else than validation. So this is like a discrete process. So we start with a model, we fit the model or we train the model on a training set, compute the validation error, and compare training and validation error. And based on this comparison, we choose another model, we make the model smaller, or we use more training data. And the end, the goal is to find this or to meet this condition. So the size of the model divided by the number of data points is smaller than 1. There's another approach. It's basically the second approach. So this one is a trial and error procedure, and this is often used. So you try a model, train, validate, look at the validation error, choose a different, and continue. And then there is like a more continuous or smoother variant, which is called regularization. Regularization. And there are 3 different perspectives on regularization, which correspond to the 3 components of machine learning. So you can regularize via the data set, you can regularize via the model, and you can regularize a method via the loss function. So let's look at the basic training problem for linear regression as our prototype of a machine learning method. So we want to minimize the squared error loss, average squared error loss on a training set. Okay. So let's say this overfits. We have in the extreme case, so let's say the extreme case, we have only 1 data point and 10,000 features of a data point. This might sound a bit ridiculous, but this might actually reflect how machine learning is applied in practice. You have a data point being me, Alex, with billions of features, like I now bought maybe some of you have also a polar heart rate sensor, and every time I do training, I get a time series on a minute interval heart rate measurements. So tons of features, but only 1 data point. So how can I learn a useful model only for 1 data point with so many features? Well, what we could do is we could we could increase the number of data points by perturbing a bit the original data point. This is called augmentation, data augmentation. So we add a bit of noise to the features. And we can draw as many random variables or realizations of a random variable as we want. So we can do a billion times. And we just get always different, slightly different features, but leave the label untouched. We could also perturb the labels by adding a bit of noise. Okay, let's say we do this with a standard deviation called square root of alpha. There's a certain reason why I call this square root of alpha, as we'll see later. And we then do, we add kind of here this additional terms, these error terms on the augmented data points. So let's call this augmented data point x10 and y10. So for each augmented data point, we get an additional error term in the training error. Y10 minus W transposed x10 squared. And you can increase M as large as you want, as many realizations you draw. So this is called data augmentation. This is one form of regularization. Another form comes naturally out of this process because you can collect these additional terms into a single term. If you say you generate these perturbations, so this call this perturbation here epsilon from a Gaussian distribution with a certain variance. Then it turns out this sum here converges to via which law? Which law can we use to replace a sum of many terms with something easier? Which law have we heard about just before? The law of large numbers. Again, so we have here a sum over many realizations, and this becomes an expectation of a random variable, and it turns out this is calculated in the lecture notes. This becomes the noise variance times the weight vector squared. All these additional terms. So what we see is data augmentation with a large number, infinitely many perturbations, becomes equivalent to minimizing the average squared error loss on the original training set, plus another term which corresponds to all these additional error terms on the augmentations, on the augmented data points, which is sigma squared times W norm squared. Did any one of you see such an optimization problem or know how this machine learning method is called? Yes.
That's rich regression.
Very good. That's called rich regression. How many of you have heard about rich regression before? Very good. And how many knew that this is equivalent to data augmentation? Very good. So I have something new for you still. Rich regression. And this is nice conceptually for me. I find this nice because I was always struggling with interpreting this term. I was teaching rich regression for a while, and I was always wondering how should I best explain this additional term. And one interpretation of this additional term is that it's all these additional error terms, squared error terms that come from these perturbations. And when you do this infinitely many times, these additional error terms here become the expectation of a random variable. And when you work out this expectation, you get exactly this penalty term of rich regression. And this also shows you the role of the parameter, of the rich parameter. It's a noise variance. So the larger this rich parameter is, which is called alpha, for example, in Python, the larger is the noise variance that you use for these perturbations. Okay, so now I told you how to do regularization via data. by augmenting data points, adding more noisy versions of the original data points. And I have showed that this is essentially equivalent to adding a penalty term to the loss function. So we have basically modified the squared error loss by adding this additional term to the loss. So what's the third perspective then of regularization? Sorry? Model, yeah. So how is this related to model? Well, it turns out that if we write this down, minimizing this training error term plus sigma squared lambda 2 has a special structure. Who of you took a course on optimization or convex optimization? Okay, so this might be something new for many of you, or maybe just a refresher. This could be interpreted as a Lagrangian term for a constraint. So this is equivalent to minimizing the what we had here, the training error. So let's write it out, YR minus W transposed XR squared. And this term here, this penalty term in the objective function, becomes a constraint, becomes W squared. So this function here, smaller or equal than some number eta, and the eta is related to the sigma squared. It's not very easy, a very trivial relation in general, but you can work out for a given sigma squared what would be the eta and vice versa. And this relation or this equivalence, this is called Lagrangian duality. This is a core of many convex optimization courses. So I highly recommend, if you have time, to take one of those courses by, I think the electrical engineering department offers them. So Lagrangian duality allows you to find out that minimizing this penalized training error, ridge regression, is essentially equivalent to training a linear model, but training a subset of all possible linear maps, in particular the subset of linear maps whose weight vectors satisfy this constraint. Okay, so now I have shown you basically 3 equivalent ways to regularize linear regression. One is by adding more perturbed data points, data augmentation, which is equivalent in the limit of using many perturbations to adding the penalty term in ridge regression, which via Lagrangian duality is equivalent to pruning the hypothesis space to make the model smaller. Okay. Yes, and that's it for today. What I wanted to tell you, just as a heads up, we will use in the next lecture on Wednesday, we will use a different regularization term for federated learning. So we will see how a specific choice for this regularization term allows to train not only a single model. So today we had a single data set and a single model. And in the next lecture, we will extend this to a collection of data sets. And for each data set, we train a personal model. And the coupling between these data sets is via a regularization term. So we will use regularization to couple the training several machine learning settings together. And yeah, so applications, I didn't talk about this in the first lecture, but now I can mention it. So, well, I ask you, can you think of applications where you don't have this single machine learning setting, but a whole collection or a network of machine learning problems? I have already hinted at one such problem. This is sports tracking. So those of you who have a sports tracker or a fitness watch, every person defines is one such data set. So each person defines such a machine learning problem because I want to learn the best fitness app for me. I want to learn the best training recommendation or diet plan recommendation for me. So you want to train a separate model for each person, individual, optimal. But still, you need to somehow use or exploit similar persons, because each one of us doesn't create enough data points. But we all together might create enough data to train a model that is also useful for me personally. And we will see how a specific choice of regularization allows to do this collaborative learning, that is federated learning. Yeah, this will be then the topic of the next lecture in next Wednesday. Okay, any other questions at this point? Yes. Statistics courses. So I will try to compile a list and send it out on my courses or on Slack. Yeah, we will not do so. What I talked today about law of large numbers is the most of probability theory that we do in this course. The rest of this course is mainly studying properties of Qs of this matrix, of such positive semi-definite matrices. So this is highly recommended that you refresh your knowledge about positive semi-definite matrices. In particular, their spectral decomposition, which is really maybe the most beautiful result in applied linear algebra that I know. Okay, any other questions? We will now in half an hour open the quiz. And yeah, let me remind you again, it might seem a bit fast-paced, the quizzes, but again, in the end of the course, you have the opportunity to review, to book a review meeting with me, and we go over all your answers to all the quizzes, and you can cover up then. So if you can answer questions there, you can re-earn the points there. So this review meeting is kind of an oral exam, but I don't want to call it oral exam. I really want you to be successful in these quizzes, because the more you are successful in these quizzes, the less I will get requests for these review meetings. So it's in my own interest, but I also want to keep it challenging. You should get a good challenging course. So, but if the quizzes might be too stressful for you, don't worry. It's not. You should not give up. In the end of the course, you get the chance to discuss in a calm atmosphere and re-earn points. But there will be no exceptions now for the deadlines for the quizzes. So the quiz opens now at 6 and ends 1 minute before midnight on Sunday. And until then, you have to start and complete your single attempt. So you have a single attempt. Once you hit the start button on the quiz, you have to complete the attempt within 2 hours. So I highly recommend that you first at least review the lecture, like the lecture notes and also maybe the recordings, and try the coding assignments. And whenever you have questions about the coding assignments, please make good use of the Slack discussion forum or sending an email, preferably to Alex P, Alexander Pavliuk. When it's about theoretical questions or the lectures, then Alex J, me. Okay, thanks a lot for your attention, and see you on Wednesday. Same time, same place.